Hello everybody, this is first lecture of composition of simple harmonic motion. So today we are going to study only basic things related to simple harmonic motion. So what is periodic motion? A periodic motion is the one which repeats itself after a definite interval of time. If a particle is performing periodic motion, it moves to and fro over the same path. Its motion is said to be oscillatory. So we are trying to understand periodic motion and oscillatory motion. Now, suppose we consider spring like this. We are considering a spring whose one end is fixed and to other end we have attached a mass m. So when the system is stationary, the position of mass m is said to be equilibrium position, or that is also called as zero force position. Now if we pull m down and let it go, it starts bobbing up and down with a definite period t. In other words, it starts oscillating about its mean position. Now, what is restoring force? From Hooke's law, we know that when a solid is deformed, it resists the deformation and it tries to regain its original position with a force that is proportional to the amount of deformation, provided the deformation is not too great. This force, it is called as restoring force, and it is responsible for the oscillations of mass m. Restoring force on a particle always acts in a direction opposite to that of the displacement of the particle. That is how we write F. It is directly proportional to minus x. Now let us take the example of simple pendulum. This is the simple pendulum which we are talking about. It consists of a heavy point mass m, which is connected by a rigid support with a inextensible string. The string is vertical when m is in the equilibrium position. Now if m is pulled aside and released, then it will start oscillating like this. Okay. Now in the equilibrium position, the downward force mg is balanced by the tension T in the string. But in the displaced position, that is in this position, tension is balanced by the component mg cos theta, and mg sin theta, it is the component of the force which tries to regain its to original position. Now in the displaced position, this is the displaced position, this is the equilibrium position. In the equilibrium position, weight mg, it is balanced by the tension T in the string. In the displaced position, we have two components. One is mg sin theta, another is mg cos theta. Mg cos theta is the one which balances the tension T in the string, but mg sin theta, it is trying to regain the original position. So this mg sin theta, it is nothing but the restoring force. So this unbalanced component is the restoring force which causes the pendulum to oscillate. For small displacements, the oscillations become linear and the restoring force a linear function of the displacement. So in general, a particle executes a simple harmonic motion when a restoring force acting on it is proportional to the displacement and acts in a direction opposite to the displacement. So simple harmonic motion is an oscillatory motion with a definite period. Now, in the above example of a spring or a simple pendulum, the particle moves back and forth in a straight line. The simple harmonic motion in these cases is said to be linear or translational simple harmonic motion. Now, this idea of linear simple harmonic motion can be extended to include angular or rotational simple harmonic motion. Now, consider the example of torsional pendulum. So, this is a system. It consists of a very light crossbar suspended at its center by a thin elastic wire. A ball of mass m is placed on each end of the crossbar. So ball of mass m is placed on each end of the crossbar. If the crossbar is given a twist about the wire, a restoring torque provided by the twist in the wire comes into play. This restoring torque is proportional to the angular displacement for small displacement. The crossbar will rotate back and forth and executing rotational simple harmonic motion. So in case of linear simple harmonic motion, we have a force which is directly proportional to x. We know that rotational analog of force is torque, and rotational analog of linear displacement is angular displacement. So simply in case of rotational simple harmonic motion, you have a torque which is proportional to minus of theta, where torque, it is acting in a direction opposite to that of the angular displacement. Yeah. Now let us talk about equation of linear simple harmonic motion and its solution. So suppose we consider a particle of mass m executing linear simple harmonic motion in x direction. Let x be its displacement from its equilibrium position at any instant of time t. Then dx by dt, that is rate of change of displacement, is the velocity, and d2x upon dt square, that is rate of change of velocity, is the acceleration at that instant t. So now we know that by the definition of simple harmonic motion, we have a restoring force which is proportional to linear displacement. Now we know that from Newton's law, force, it is nothing but mass into acceleration, that is proportional to minus x. Now we know that acceleration, it is nothing but d2x upon dt square. So that is proportional to minus x. If I remove the sign of proportionality, I can write m d2x upon dt square, that is equals to minus kx, where k is the constant of proportionality. So negative sign here indicates that restoring force acts in a direction opposite to the direction of the displacement. K is called as force constant and is equal to magnitude of restoring force per unit displacement. Now instead of this system, if we consider a system of spring, if we consider a spring system, so in that case the same k which we are calling as a force constant, that same k in case of a spring system, it is called as a spring constant or stiffness constant. Now above equation, we have d2x upon dt square equals to minus omega square x. So we can shift that minus omega square to LHS, and we will get d2x upon dt square plus omega square equals to x equals to 0. Now suppose we assume omega square, we have replaced k by m, instead of k by m we have substituted omega square. So where omega is root of k by m. Now suppose the solution of this equation, it is of the form x equals to a sine omega t plus phi 0. Now here, what is a? A, it is the amplitude. What is amplitude? Amplitude, it is the maximum value of the displacement. Maximum displacement of the particle is called its amplitude. What is omega t plus phi 0? That is called as the phase of the particle at time t. And suppose we take into consideration only phi 0, that is nothing but the initial phase, or it is also called as epoch of the particle. Now omega, when we talk about omega, it has dimensions of reciprocal of time, that means it is frequency, and it is called as angular frequency of the particle. Now we have two things, one is natural frequency, another is angular frequency, and they are related to each other by the equation omega equals to 2 pi f. So f, it is nothing but omega upon 2 pi, and if we substitute the value of omega, we will get 1 upon 2 pi under root k by m. And we know that frequency and time period, they are reciprocal of each other. Once you know frequency, you can just take reciprocal of both sides, and you will get t equals to 1 upon 2 pi, it will be 2 pi, under root of k by m, it will be under root of m by k. So since the solution of equation of SHM can be written as a sine function, this simple harmonic motion, it is also called as sinusoidal motion. So this is all the basic related to simple harmonic motion. In our next lecture, actually we will start with the topic, that is composition of two simple harmonic motions.